In this video, we're going to define the definite integral. Now, the definition of the definite integral is if f is a continuous function defined on an interval a to b, we divide the interval ab into n subintervals of equal width. Now that's the process we looked at in the previous video of finding the widths of our rectangles. So we let x sub 0, that would be equivalent to a, x sub 1, x sub 2, all the way up to x sub n, and x sub n would be at b, be the endpoints of these subintervals, and we choose sample points in that interval. Now we discussed that it doesn't matter if we choose the left side of the rectangle, the right side of the rectangle, or any value between those. In these subintervals, x sub I lies in the ith subinterval, then the definite integral of f from a to b is defined as what we see here. So notice what we have. We have the limit of the summation from I equals 1 to n as n goes to infinity of f of x sub I times delta x. And we know f of x sub I is the height of our rectangle, delta x is the width of the rectangle. So if we let the number of rectangles be n, and then we take the limit as n goes to infinity, we'll find the area under the curve on the interval from a to b. So this is defined as this interval, this integral from a to b of f of x dx. So as we've been going through this process, we've been finding the area under the curve, and that's the definition of a definite integral. We're finding the area under the curve from a to b. Now let's define some things here. We have the integral sign. It looks like that big S. That's called the integral sign. The integrand is this f of x. Our lower limit of integration is at the bottom, and the upper limit of integration is at the top. Now the process of calculating this integral is called integration. So the definite integral of f of x dx from a to b is some number because it represents the area under a curve. It does not depend on x. If f is continuous, then the limit in our definition always exists, no matter how we choose the sample point. If we use the left side of the rectangle, the right side of the rectangle, or any point in between. The notation that we have been using is called a Riemann sum. Now this is just the summation of f of x sub I times delta x. That's the width times the height of each one of these rectangles. When we add them all up, we call it a Riemann sum. So here's an example of a Riemann sum from 0 to 2. This estimates the area under the curve. Notice our function is greater than 0. It's above the x-axis. And so we can sum up these rectangles to represent the area under the curve. Now if we have a function greater than 0, the integral from a to b of f of x dx is the area under the curve. That will find us the exact area under this curve. If a function takes both negative and positive values, then the Riemann sum is the sum of the areas that lies above the x-axis and the negatives of the areas of the rectangles that lie below the x-axis. So if we are looking for the area of the curve from a to b, notice we have the function is above the x-axis from a to 2, but then below the x-axis from 2 to 6. And then again above the x-axis from 6 to b. So here, in this case, we would define this as being the net area because we would add the positive areas and then subtract off the negative area. So that would give us the net area. Here's an example. Express the limit as an integral on the interval from 0 to pi. So if we wrote this as an interval, we know that our function would be x cubed plus x sine of x. Because think back to when we set up our Riemann sum, we would have the integral, let me change that color. We would have the integral from I equals 1 to n. We would take the limit as n goes to infinity of our f of x sub I times our delta x. So we are just plugging x sub I into our function. So if we look at this x sub I here, we can see we have an x sub I cubed plus an x sub I times the sine of x sub I. So we can see the function simply would be x cubed plus x times the sine of x. Okay, if we're going to write this as an integral, we need our function and we need the interval. Well, we can see that the interval is right here. So we would have our integral from 0 to pi, and our function is x cubed plus x times the sine of x. And then here, remember, our delta x is the width. That becomes dx in our integral. That represents infinitely small widths of these rectangles, or our subintervals are infinitely small. So this would be our integral on the interval 0 to pi for this function, and we'd be finding the area under the curve. Let's look at evaluating integrals. Here are three little formulas that we need to be familiar with when we're working with Riemann sums. And the first one I'm going to explain a little bit, and then I'm just going to ask you to accept the following two, as we could do the same type of process, but we're not going to go through the process. This right here, if we are looking at summing up from I equals 1 to n of I, that means we plug 1 in for I, plus, then we plug 2 in, plus, then we plug 3 in, plus, then we plug 4 in, all the way up to n. So this just represents the summation of our integers. Well, if we're looking to sum integers, if we have 1 plus 2 plus 3 plus 4 plus, let's say, all the way up to 100, I could reverse the order of the numbers and then add it to what I have. I forgot my 98 here. 97 plus all the way down to 1. So if I added all of these up, I'd get 101 plus 101 plus 101 plus 101. Now I have 100 of these 101s. So if I multiply those together, that will give me the sum here of all of these numbers. But I'm adding this one plus this one. So that gives me twice as much as I need. So I'm going to divide this by 2. And that would give me the sum of the first 100 integers. Now if we did the same thing in general here, we would have n times n plus 1, just like we did here. We had 100 numbers, so we have 100. Here we have n numbers, so we have n, times one more than n. Here's n plus 1. And then we would divide the whole thing by 2. So that's where this little formula comes from. The summation of I from I equals 1 to n equals n times n plus 1 all over 2. And as I said, I'm going to ask you just to accept these two. We're not going to show why those equal what they do. But we are going to use those when we work with these Riemann sums. So we need to be familiar with those. Now here are some rules when working with sigma notation. Let's look at this first one. If I have, let's take for example the summation from I equals 1 to, let's say, 10, and I'm summing up the number 4. So I'm just representing this with some numbers. This would equal 4 plus 4 plus 4 plus 4. We'd have this 10 times. So another way to find this would just be 4 times n, the number we have up here. So if we are ever summing up a constant from I equals 1 to n, the sum is just going to be this constant times the number of times we're finding that value. Here, for the next one, this is just indicating if c is some number, we can pull that number out front and sum all of these up and then multiply it by c. The next one just indicates we can break apart a Riemann sum that we have terms being added here. We can break it into pieces, find those two separately, and then add them. And likewise for subtraction. Evaluate the Riemann sum for x cubed minus 6x, taking the sample points to be the right-hand endpoints, and a equals 0 and b equals 3. And we're going to use n equals 6. So we'd have 6 rectangles. Then we're going to evaluate this integral. Now, if we find the Riemann sum of x cubed minus 6x on the interval 0 to 3 with n equals 6, that will be an approximation for this integral. Now, the integral gives us the exact value under the curve. But when we let n equal some number, as in this case, and we look at the Riemann sums, we're going to just get an estimate for the area under the curve. Now, to find the width of each one of these rectangles, we're just going to take the length of the interval, which is the length of the interval. If we have some function here from a to b, we're trying to find the area under the curve, we're going to take the length of this interval and divide it by the number of rectangles. Well, the length of that interval is b minus a divided by the number of rectangles. That's how we get our delta x. So that would give us, in this case, b equals 3, a equals 0, so we'd have 3 minus 0, and we're going to divide it up into 6 equivalent rectangles. So each rectangle would have a width of 1/2. Now the right endpoints, if we're using the right side of the rectangle, these are the points we're going to be using. So for instance, if we have our, let me start this at 0. So let's say this is our curve, and we're going from 0 to 3. We're breaking this up into 6 rectangles. So 1, 2, 3, 4, 5, 6. Now, if we're using the right side of the rectangle, we know that this width right here would be 1/2. And that's where we're getting this value right here, x sub 1 equals 0.5. That's the value we're going to plug into the function to get the height of that rectangle. Now this value, we just add another 1/2, so that would be 1. That's the value we're going to plug into the function to get the height of this second rectangle. And that's our x sub 2. And so on. Here's our Riemann sum. We're plugging in 0.5 to the function times the width, delta x, which we found to be 1/2, plus f of 1 times our delta x, plus all the way up to 3 times our delta x. So this would represent the estimate for the area under the curve from 0 to 3 using 6 rectangles. So if we plug 0.5 into the function, our function is x cubed minus 6x. So we'd plug in 0.5 for all the x's, and then we would find f of 1, plugging in to our function x cubed minus 6x, we would get the next value, and so on. Now we did factor out the 1/2 because the delta x above is 1/2 for each one of those terms. So we just factored it out front. So the first term in the parentheses, the negative 2.875, represents f of point, and that's 0.05. It should be 0.5. The next term is f of 1. If we plugged 1 into the function, we would get -5, and so on. So this would give us the estimate for the area under the curve. So let's look at the graph. This is what we have found. There are the rectangles that we have used to estimate the area under the curve. Now this is a net area because we have part of the function is below the x-axis, part of it is above the x-axis. Okay, the second part of the question is this time we're going to let the number of rectangles be n. So our interval was 3 minus 0, but the number of rectangles this time is n. So our delta x is going to be 3 divided by n. So using the right endpoints, we would actually be starting at 0.5. But since this is starting at 0, this actually is going to be representing using the left endpoint. So for what we're doing here, we're going to be looking at using the right endpoint. And so if we use our right endpoints, we know that our x sub I using our formula, we know that x sub I is found by taking a plus delta x times I if we're using the right endpoint. If we're using the left side of the rectangle, we use a plus delta x times I minus 1. So we are going to be using the right side of the rectangle, so we're going to be using this formula. So to find our x sub I, Our starting point is at 0, so we'd have 0 plus, here's our delta x, 3n times our I. So this is just 3I over n if we're using the right endpoint. So now let's plug this information into our Riemann sum. We would have the limit, we're going from I equals 1 to n as n goes to infinity. And now we're plugging our x sub I into our function. Well, our function is x cubed minus 6x, and our x sub I is this. So we would have 3I over n cubed. See here, that's where I've plugged that in, minus 6 times, now we're plugging in 3I over n for this x in minus 6x. So that's what our Riemann sum would look like at this point. Now if we cubed the quantity, we'd get 27 over n cubed, I cubed minus 18I all over n. The idea here is to isolate those i's in front of your sigma notation, and then we can change those into terms of n. So here we've isolated the I cubed. Now, if you want to think about it this way, we're just taking this quantity right here and we're taking it out front because this is considered to be a constant, because we're looking at I going from 1 to n. So the only thing that's changing is I. So that's a constant, and this we could consider a constant also. So we could take this out, and when we separate these as two different summations, we would have to multiply this 18 over n times this quantity also. That's where we are getting this quantity. Now we have a limit to solve. Now we are changing our, remember when we said this piece right here, we said we could change this into n times n plus 1 all over 2 squared. We can also change this into terms of n only. We know that is equivalent to n times n plus 1 all over 2, this quantity here. Now we can look at evaluating our limits. So if we evaluate this limit, we get negative 6.75. So here's a graph of the function x cubed minus 6x. And we have found the net area was negative 6.75. Riemann sums. Now, if we use 10 rectangles for the last example, our x cubed example minus 6x, this is what the 10 rectangles would look like. If we used 40 rectangles, this is what it would look like. You can see the amount of error is minimized by increasing the number of rectangles. And here's a table. If we used 5,000 rectangles, you can see we would get an area of negative 6.7473, which is very close to the area that we found using the integral negative 6.75. Set up an expression for the integral of e to the x dx from 1 to 3 as a limit of sums, and then evaluate with a computer. If we were to look at this as the limit of sums, our function is e to the x and our interval is 1 to 3. We can see that from the upper and lower limits of integration on the integral. So calculating our delta x, we'd have 3 minus 1 over n, so 2 over n is the width of each rectangle. And our x sub I, since our starting point is 1, we would have 1 plus 2i over n for our x sub I. Writing this as a Riemann sum, now plugging in our x sub I to our function and changing our delta x to 2 over n, pulling out the 2 over n in front. It's just a constant. It's not changing as I goes from 1 to n. And then using our function e to the x. So we're plugging our x sub I into the e to the x to get e raised to the 1 plus 2i over n power. Now if we evaluated that with a computer, we would get e cubed minus e.